You, and you. That's our you, Ben fam. That's right, right there, you. So you all use a computer, whether it's at home, at school, or even in the bathroom. I see you, Sam. I know you use it in the bathroom. You're guilty. So, let's get the facts straight. You all use a computer for slogging through Instagram, looking at Gmail, going through YouTube, doing homework assignments, and you don't even know how to build a computer or how it works. Well, here, I want to teach you about how one computer works. You're going to go from being a person who doesn't know how to use the thing you use the most to a person who knows everything, which is basically means you're going to reach enlightenment when watching this 10-minute video. Or as Archimedes says, Eureka!
Computer is one of the marvelous inventions of the recent times. Computers are used to watch games, watch educational films, it's used to do homework, used to browse the internet, and used to code applications that can be used to perform a task. The whole history of computing can be divided into 5 main generations. The first generation was 1951 to 1958, where vacuum tubes were used as the basic component for memory and CPU. They were very large in size and consumed lots of power, and emitted too much of heat. They required to be housed in large air-conditioned rooms. The period of the second generation was 1959 to 1964, where computer transistors were used. The transistors were highly reliable and easier to maintain than the vacuum tubes, and replace them. They require much less power. Few issues where huge cooling systems was required, only used for specific purposes, and punch cards were used for input. The third generation was 1965 to 1970, where silicon transistors replaced germanium transistors. Integrated circuits were developed by interconnecting transistors, resistors, and capacitors, grown on a single chip of silicon. Chips were small in size, less power consuming, and less expensive than the previous technology. The fourth generation was 1971 to 1989, where computers were made using very large-scale integration technology. Tens of thousands of components were packed on a single chip, the size of a fingernail. It led to the development of microprocessors. Personal computer operating systems were developed during this period. The fifth generation is 1990 onwards, where very large-scale integration technology gave way to ultra-large-scale integration that led to the development of microprocessor chips with several million electronic components on each. Powerful laptops, notebook PCs, and desktops were the other developments during this period. Technology has transformed vacuum tubes that occupied the entire room to a laptop that can be held in your hand. Now, let's talk about the different components of the laptop and the uses of each of the components. First, the display screen. It is used to display output to the user in desired format. Keyboard is the most common input device used to provide commands or data to the laptop or computer. That's what you see on your laptop daily. Cooling fans. It cools down the temperature of the internal components such as CPU, GPU, and etc. RAM is a short form of random access memory. It is a chip with temporary memory which stores data and program while they are being used and requires power source to maintain its integrity. A hard drive is a hardware device that permanently stores and retrieves data on a computer. Recently, they are coming in chips. CPU, or aka the central processing unit, is the brain of the laptop. It is a chip in a computer that executes all the instructions from the software. A motherboard is a circuit board inside computers that stores electrical components such as CPU, GPU, RAM, and etc. It also helps them interlope and communicate. Battery. It is the power source or the power backup in order to operate laptops when AC main power is not available. So all these components combine together and form the laptop, and each component has chemistry associated with it. Now, let's focus on the chips manufacturing. These chips have nanoscopic transistors. Each of these chips, with the size of an ant, has millions of transistors that are manufactured in huge labs called clean rooms. And these clean rooms have tools to fabricate these chips that are really expensive. Operators cover the body to prevent particles falling onto the wafers. These clean rooms are 100,000 times cleaner than any operating theater, and as big as 10 to 15 football pitches put together. Can you believe that these chips are made from sand? Well, better believe it, they are. Sand combined with CO2 and melted in crucible and solidified to produce 99.9% silicon rod called ingot. These are sliced into discs called silicon wafers. This results in a perfect silicon lattice arrangement shown here. To build transistors, several steps needed to be repeated. Let's start with photolithography. Just like you draw a blueprint to build a building, you draw circuit designs onto a wafer, which is called photolithography. Very similar to a photo taken on a film of a camera. The photomask functions just as the film. In order to draw a circuit on the wafer, photoresist is coated and light is passed through a mask. When light hits the wafer, it reacts with the photoresist and bonds are broken. Then the photoresist is developed just like developing a photo using a developer solution which reacts with the photoresist and dissolves it. The cartoon shown an example where photoresist molecule structure is converted to a soluble molecule with light and baking shown in the first two reactions here. Selected areas are removed by either wet or dry etching. Plasma etching, also called as dry etching, where reactive gases are introduced and these energetic species remove the surface atoms. The reactive species are formed due to plasma and react with surface atoms to form volatile compounds, which are effectively pumped out. Another type of etching is a wet etch, where a solvent is poured on the wafer and it reacts with the surface atom, and the soluble product is removed effectively later on. Film deposition is where super thin films are coated using the process called chemical vapor deposition. An example of deposition of a metal by reacting metal chloride molecules with hydrogen at high temperature shown here. The reaction happens on the surface to form metal on the surface and hydrogen chloride gas, which is the waste gas. The waste gas are pumped out of the chamber, and this repeats until you form a film on the entire wafer surface and form a desired thickness. Doping silicon doesn't conduct electricity, but when you inject ions called dopants into silicon, they become conductive. These ions distribute randomly in the silicon lattice at high temperatures. Next is packaging. The wafer is cut into individual chips and placed onto a PCB board. These are then wired bonded to the external electrical connections. The different type of chips like CPU, GPUs, memories, etc. are fabricated using a very similar process I described. Batteries in a laptop are made of thin lithium ions. At the anode, lithium is stored between layers of graphite. Lithium likes to give away its valence electrons and separate from the lithium and goes to the cathode. Lithium becomes positively charged ion. Law of lithium ions leave and electron flow is built up at the cathode. Cobalt has positive charge and needs electrons. With time, cobalt becomes more negatively charged and electrons resist this motion. To fix this, add an electrolyte which allows lithium ions to pass from anode to cathode, but not allowing electron flow. Here is the chemical reaction. Now when the battery loses charge and needs to recharge, USB chargers applies more force on the electron flow in the opposite direction, out of the cathode. Exactly opposite to earlier scenario, which is why it is rechargeable. Inside the laptop, there's a heat pipe placed between the processor and a fan. Inside this heat pipe, there's a small amount of liquid and a wick. When the processor heats up, it causes the liquid inside the wick to evaporate. The vapor moves to the opposite end, which then cools down by a fan, and excess heat is removed. This causes the vapor to condense to a liquid. This liquid flows back along the wick to pick up more heat, and the cycle repeats. The condensing phenomenon can be seen in our everyday life. For example, climate cycle, evaporating water from lakes and then vapor rising to form clouds. When the water vapor gets cold enough, it drops to the ground as a rain, snow, or even hail. The chemistry is used in most of the parts of a laptop. Major chemical reactions happen during the manufacture of semiconductor chips, like CPUs, GPUs, storage, memory, etc. Chemical reactions occur during a charging a battery of the laptop. Chemical changes happen during cooling the laptop.